Welcome. In our previous video, we introduced the concept of query optimization. We spent a considerable amount of time looking at a B tree and discussing the structure of that tree and the access methods supported by a B tree. After discussing that data structure, which is used for indexes, we then turned our attention to looking at what is query optimization. We discussed some concepts associated with query optimization and walked through simple hypothetical scenarios in terms of the content of a table and questions being asked. We explained the difference between rule-based optimization and cost-based optimization. So with that background, we're now going to examine cost-based optimization in a bit more detail. We'll be taking a look at a set of data with some statistics available to us and describe different scenarios that could possibly be used as execution plans to answer a question posed against this database. The query will actually involve 3 tables, so we'll discuss different ways that these tables could be accessed. All these different approaches that we discuss will produce the same result. However, the path that we take to get to producing that result will be significantly different. This should give you a much better idea of what query optimization is about and some of the challenges that are faced or presented to the query optimizer. So let's get underway. We'll begin our examination of query optimization in some detail by looking at a paper that was written back around 1984. The title of the paper is Query Optimization in Database Systems. Information about this resource can be found at the end of our lecture topic. Although this paper is an old paper, it presents some very valid points and provides some good illustrations. The authors begin by saying, query optimization tries to solve the problem by integrating a large number of techniques and strategies, ranging from logical transformations of queries to the optimization of access paths and the storage of data on the file system level. Their comment refers to logical transformations, and this is quite relevant and quite important when considering SQL, because SQL allows us to ask a question in various ways. This is similar to expressing some thought or idea in a natural language such as English. For example, we might convey the notion of some action that has occurred by saying, John kicked the ball. Alternatively, we could express the same general idea with a different sentence. The ball was kicked by John. While the two statements serve to convey the same general information, they are expressed in different ways, but the underlying semantic information is essentially the same. A similar situation arises with relational database queries. 2 tables can be accessed through a join or a subquery. Consider accessing the staff and department tables with a join, and we retrieve only data from the staff table. Consider an alternative where we accomplish the same result by phrasing the question a little differently and using a subquery. These queries produce the same result, but the questions are phrased differently. Our concern with query optimization goes beyond the 2 forms producing the same result, getting the same answer. If the questions are semantically equivalent, does answering the question result in the same amount of resource being consumed? That is there a difference in the performance of the 2 queries? Remember, we're saying they're asking the same question, they produce the same result. Is one more efficient than the other? If there is a difference, then a user who presents the question in one form would be penalized by experiencing greater resource consumption and a longer response time. This is where the concept of a logical transformation comes into play. The optimizer should be able to recognize that these are two logically equivalent queries and produce the same result, but do it in the same way. That is, the same execution plan should be produced. One additional point before we move forward. Before continuing, we should note that the term query optimization is actually a misnomer. It is not practical and may not be possible to achieve an optimal execution plan for a query. We have only certain statistics available to us, and we are limited by a need for a quick response time. Thus, the authors of the paper address the issues of minimizing total cost of query processing. They bring to our attention the concern of what resources contribute to this cost: communication, secondary storage access, storage, computation. They note that the structure of query optimization algorithms is strongly influenced by trade-offs among these cost components. And we'll see this point stressed as we look at some examples provided by the authors of the paper. The authors use the following schema, consisting of 5 tables, to present the idea that there are different execution plans that can be used to execute a query. We'd like to draw your attention to departments, courses, and lectures. These 3 relations or tables will be utilized to answer the question presented at the bottom of the slide here. That is, we wish to identify the names of departments located in New York offering courses on database management. The primary keys in these tables or relations are indicated by underlining the attribute or attributes that determine the key. Let's take that query, but before we run it, present you with a little bit of information that can be quite useful for an optimizer or for anyone trying to develop an execution plan for that query. The statistics used by the optimizer could be explicitly stored in the catalog or derived while making decisions regarding the execution plan. The information that we're showing here in our bulleted list can be used by the optimizer. One comment about this paper. The paper was written in 1984. The authors point out that the information that they're suggesting here is usually not available to the optimizer. I'd like to amend that comment by saying that with modern systems, they tend to have such information available, but their point is well taken. The department relation consists of 100 departments. 5 of them are located in New York. A physical record or a block can hold 5 department records or 50 department name values. There are 500 courses, 20 of them on the subject of database management. A block can hold 10 course records. There are 2,000 lectures in this database, 300 of them on database management. 20 satisfy both conditions, and these 20 come from 3 departments. A physical block, once again, can hold 10 lecture records. Sorting time, again a performance factor on the system, is n log n, where n is the size of the file in blocks, and there is a buffer of 1 block for each table. All tables are physically sorted by ascending key values. In the following discussion of alternative strategies to execute the sample query, ideas behind query optimization will be presented, and this will justify the study or the investigation of this process of query optimization. So the discussion of strategies indicates secondary storage accesses required to read and write a physical block. The first strategy they suggest would be to form the Cartesian product of courses, lectures, and departments. Before we discuss this, remember that a Cartesian product says that we're just slapping the rows together from these different relations or tables. There's no relationship that is being exploited or utilized to connect the rows. So we're going to get a lot of data produced, and much of it will not be very meaningful. So in forming the Cartesian product, we should note then, based upon the record size and the number of blocks, that there will be 50 blocks from courses, 200 blocks from lectures, and 20 blocks from departments. This is where their suggested number of reads of 200,000 comes from. Multiply 50 times 200 by 20. They then say that once you've amassed all of this data, retain the department name column of the department rows for which the course number of course and lectures match, the department name of lectures and departments match, the course name is equal to database management, and the city is New York. And the result will be a single write. So approximately 200,000 I/O operations are needed to accomplish this query following this execution plan, which uses cross-product or Cartesian product. As an alternative to a cross-product, performance can be improved by considering only those combinations of elements from different relations that have matching values in common attributes. Using existing sort orders, combinations can be formed by merging the participating relations. This is the join operation, and this is what we'll see presented in strategy number 2. But to summarize what strategy 1 did, it generated an intermediate result, a very large intermediate result, of which only a small portion was actually relevant to further processing. So we're looking to perhaps refine this in some way and perhaps reorder operations. So with strategy 2, it says let's merge the courses and the lectures. Well, that'll be 50 reads plus 200 reads, and we'll end up with writes of 400. Then sort the result by the department names. And again, because of the sort, we see n log n, and we have 400 blocks, and that attributes then for the read and the write operations for step 2. Step 3 says to merge the result with departments. Step 4, select the combinations with the city equal to New York and the course name equal to database management. And finally, keep only the department name columns. Ends up with a total of about 6,000 accesses, considerably fewer than what we saw just a moment ago. But there's a third possible strategy that they suggest, and this will demonstrate further refinements by performing value-based selections early to reduce the cost for sorting and merging of intermediate results. So we merge courses with lectures. We keep only the department names of combinations with CNAME or course name equal to database management. Then we sort the department name list that was generated, merge the results with departments, and keep only the department names that satisfy city equals New York. And we've reduced this considerably. Now we're down to 277 accesses. While the example execution plans that we've discussed thus far have been hypothetical, let's now consider how queries might be processed in an actual relational system. And we'll use Oracle Database to examine how a query optimizer produces an execution plan. Consider the query that we're presenting here, where we're selecting columns from the staff table and the department table, and expressing a relationship between the tables to form a join. So how might the optimizer process this query? Well, to accomplish its task, the optimizer constructs an execution plan, which consists of one or more steps. Each step will either access a new database object or process data from another step. A set of rows returned by a step is referred to as a row source. Because the steps are related to one another, we can actually show a representation of the execution plan as a tree. The shaded areas in our diagram indicate steps which retrieve data from the database. These are access paths. The unshaded steps indicate steps in the execution plan which operate on row sources. We indicated that the query we just presented performed a join. It turns out that most relational systems have more than one way to accomplish a join. They can combine rows from two row sources using a nested loops join, a merge scan join or sort merge join, or a hash join. Note that a join operation will combine only two row sources. Remember that the join is a binary operation, as we discussed in the relational algebra. If an SQL statement references more than two tables, the tables, or the row sources, will be accessed in pairs. So how do we know which join method was actually employed when a join was performed by the system? Oracle and other systems provide a statement called explain plan. With explain plan, you present a query to the database system, to the SQL processing engine, which is actually going to be evaluated by the query optimizer. And the optimizer will examine the query, and it will go through the motions of formulating an execution plan. But it stops at that point. The SQL processing engine does not actually go ahead and execute that strategy. It simply lets the optimizer say, this is how I would do it. The syntax for this statement in Oracle begins with explain plan. Then we introduce the SQL statement that we wish to have analyzed. What the explain plan statement does is to capture the steps of the execution plan and place these steps as rows into a special table called the plan table. We can then examine these steps by running a query against the plan table. For Oracle database, we are conveniently given a package called dbmsxplan with a few different routines, one of which is called display. Using a query similar to what I've presented here, we can extract the information from the plan table and view the steps in a logical fashion to see exactly what decisions were made by the query optimizer. An interesting point brought up here is that the execution plan indicates how a query is executed or is proposed to be executed, but it does not reveal the actual resources consumed by following the steps in that plan. There are other utilities that a database system provides to do an analysis of a statement which has actually been executed to determine the resource consumption. We mentioned three common ways that a join could be accomplished. These are referred to as join methods. Let's take a closer look at the characteristics of these different join methods and what causes the optimizer to choose one method over the others. A nested loops join involves the following steps. The optimizer first designates one of the tables as the driving table or the outer table. The other table will be called the inner table. For every row in the outer table, all rows in the inner table will be accessed. The outer loop is performed for every row in the outer table, and the inner loop will be performed for every row in the inner table. This technique tends to be good for quickly retrieving the first row of a result set. In just a few logical I/O operations, data will be returned to the application. The outer loop is the driving row source, so the order of tables in the execution plan is important. The outer loop produces a set of rows for driving the join condition. The outer loop will look something like what we're showing here in the execution plan. It will be designated as nested loops, and there will be the outer loop, and embedded within that, the inner loop. So the inner loop is iterated for every row returned from the outer loop, ideally by an index scan. If an access path for the inner loop is not dependent on the outer loop, the result is a Cartesian product. This means that for every iteration of the outer loop, the inner loop produces the same set of rows. Take a look at an actual example. Here we're joining staff and department. Of course, in the SQL statement, we don't specify the join method. That is a decision made by the optimizer. But when we do the explain plan and examine the execution plan, it's revealed to us that nested loops was the method employed for this particular join. So on line 1 of the execution plan, we see nested loops. Indented beneath that would be the table access for the staff table, and beneath that, the table access for the department table. But note, embedded or indented below step 3 is another step. These indentations are actually showing parent-child relationships. Remember, we showed that this idea could be depicted as a tree because of the hierarchical association between the nodes or between the steps within the execution plan. Thus, step 4 would be executed prior to step 3. The index would be scanned, the PK department index. The index on the primary key would be scanned to obtain the department IDs. These department IDs could then be used to access the actual rows within the department table. Note, step 4 also has a footnote. It specifies that staff DEPT equal department DEPT was the motivator for the access to the index in step 4. In this example, the staff table is the driving table. The table scan of staff forms the outer loop. The inner loop contains access to the department table. Thus, as we obtain a row from the staff table, we then probe the department table to find a match. But we don't look at every row. We take the department ID from the staff table and use that as the search argument to do the unique scan of the PK department index. We then find the row ID, which is mapping to the location of the row within a department table, and retrieve that row and form the join. Now let's consider the hash join. A hash join consists of two phases. One phase is called the partitioning phase. Here, the smaller of the two tables is used to build a hash table on the join key. and this hash table is placed in main memory. Again, the statistics available to the optimizer tell the optimizer which of the two tables would be the smaller table. In the second phase, we refer to this as the probing phase. The larger table will be scanned, probing the hash table to find matches. Effectively, the hash function is being invoked with the join key from the larger table, or say from rows from the larger table. And when we have a collision with the hash table in memory, then we have a match. The in-memory hash table consists of an array and linked lists. When the join column of a row is hashed, the hash identifies an entry in the array. This is our hash table. The array entry is the head of a linked list. Because the hash function may result in collisions, a linked list is used to hold rows that hash to the same array entry. The following processes will actually occur after we've built the hash table in memory. The second, or the larger table, is scanned. It's broken up into partitions, like the smaller table, and the partitions are written to disk. A hash join is used to join two tables using an equijoin, and if either of the following conditions are true: a large amount of data needs to be joined, a large fraction of the table needs to be joined. A hash join then is best used when the smaller table fits in available memory. The cost is then limited to a single read over the data of the two tables. The hash join can still be used even if the smaller table does not fit entirely within memory. The system would use external storage. Here's an example of a join involving staff and course, which produced an execution plan involving the hash join. In step 2, we see a full scan of the staff table. This turns out to be the smaller of the two tables. This could be validated if we included a little bit more information from the plan table, which would be the number of rows and the number of bytes. Because the staff table is listed first, this is the table for the partitioning phase. The course table listed second is involved in the probing phase. We have presented the mechanics of the hash join. Let's now be clear as to how it applies to an actual join. We are joining the staff and course tables based on the values in the eSalary column of staff and the values of the CLab fee column of course. The condition is equality, that is, an equijoin. The entire staff table is read to produce the hash table. So why do we read the entire table? Because we do not know a priori which values will find matches in the other table. Thus, we need to ensure a hash table entry for all values present in this table. We then read the entire course table. One by one, the lab fee values found in this table will be used to hash into the hash table. This is how we compare lab fee to eSalary. When the hash results in a collision, we have found an equal value. The row from course that contributed the matching or colliding CLab fee value will be joined with the row from staff whose eSalary value resides in the hash table slot. So why is this join method efficient? Because we read each table only one time. A table scan can be efficient if we are able to read multiple blocks with a single I/O operation, something referred to as a multi-block read. This ability is controlled in Oracle database by a system parameter setting. And now our third join method, the sort merge. Sort merge joins can be used to join rows from two independent sources. Sort merge joins are useful when the join condition between the two tables is an inequality, such as less than, equal to, greater than, or greater than equal to, but not a non-equality. Sort-merge joins perform better than nested loop joins for large data sets. Hash joins generally perform better than sort-merge joins. However, sort-merge joins can perform better than hash joins if both of the following conditions exist. The row sources are sorted already. A sort operation is not required. An index could be used to access rows in order. A merge join does not involve a driving table. This type of join consists of two steps. First, we must have the data placed in the proper order. So a sort operation is performed. Both inputs are sorted on the join key. Then a merge operation is applied. These two sorted or ordered lists are merged. A sort join operation is not performed for the row source if the input is already sorted by the join column. If a sort merge join involves choosing a slower access method, such as an index scan as opposed to a full table scan, the benefit of using a sort merge might be lost. In this example, two independent tables, staff and course, are being accessed. And notice the relationship that's being expressed, the join condition, is an inequality. This prompts the system to consider the merge join. Observe that what happens is within the merge join, one table is sorted, the other table is sorted, and the output of the two sorts are then used to perform the actual join or merge operation. So the optimizer can choose a sort merge join over a hash join for joining large amounts of data if any of the following conditions apply. The join condition is not an equijoin. Remember, that was the key criteria for determining if a hash join qualified. Sorts required by the other operations make it cheaper to use a sort merge than a hash join. The idea is that if you would need to sort for a later operation, such as an order by, then why not do the sort up front and achieve the potential benefit of the sort merge join? Additionally, the work areas that are used, what are called hash areas and sort areas, internal memory structures, if these are set inappropriately, they can make the cost of a hash join appear to be higher than a merge join. The optimizer estimates the cost in selecting a join method in the following ways. The cost of a nested loop join operation is based on the cost of reading each selected row of the outer table and each of its matching rows from the inner table, bringing these into memory. The optimizer estimates the cost using statistics in a data dictionary. Remember, query optimization does not necessarily produce an optimal execution plan. It generally produces a good or efficient execution plan. And this is the result of these statistics contributing to estimation. The cost of a sort merge join is based largely on the cost of reading all the sources into memory and then sorting them. And the cost of a hash join is based largely on the cost of building a hash table on one of the input sides to the join, and then using the rows from the other to probe that table. So the optimizer considers the factors that we've mentioned here, plus additional factors when determining the cost of each operation. A smaller sort area size is likely to increase the cost of a sort merge join because sorting cannot be completed in main memory, but would have to be done within secondary storage as well. because of the size of the data. So this would contribute to greater CPU time and I/O time if we have small sort areas. A larger multi-block read count is likely to decrease the cost for a sort merge join in relation to a nested loop join. So if the database can read a large number of sequential blocks from disk in a single I/O, then an index on the inner table for the nested loop join is less likely to improve performance over a full table scan. The multi-block read count is again specified in Oracle through a system parameter. Although much more can be said about query optimization, you should now at least have an appreciation for the challenge faced by the optimizer in arriving at an efficient execution plan. Let's go a step further and look at overall SQL statement processing and put optimization within its place in this sequence. There are 4 phases involved in statement processing. The first is parsing, then we see optimization. This is followed by the actual code generation, and finally the execution of the statement. Well, much discussion of statement processing relates to the execution of a single statement. You must be aware that in practice, statements are often not executed in isolation, but share resources with other statements executed concurrently. So there are additional factors that can influence the actual execution of a statement. We've been addressing the idea of looking at a statement and arriving at an execution plan based on the objective of that statement. But in terms of actual performance, there are other factors that must be considered. During the parse phase, the statement is subjected to a syntactic analysis. We validate the syntax to say that this is a well-formed expression. A single SQL statement may have many query blocks. A predicate could include an operand, which is itself a query, another query block. So a query block is represented by a select list, the items to be retrieved, the from list, the tables or data sources to be referenced by the query from which the data will be retrieved, a where clause, a Boolean combination of single predicates. If parsing is successful, then the optimizer is invoked. The optimizer assembles facts about the object that have been referenced in the query and verifies that these objects are valid objects, that they do exist. There's metadata about the objects within the system catalog. We're looking at the names of the objects, the names of the columns, the data types of the columns, and the sizes of the columns. Semantic checks are performed. For example, if we're looking at data type compatibility, are you going to take a name and multiply it by an address? That doesn't make any sense. It's incompatible. That's a notion of a semantic check. The metadata is searched through a process we'll call catalog lookup to obtain the statistics about the object that are referenced and the available access paths, including the presence of an index, for example. The optimizer then performs the access path selection. It first determines the evaluation order among the query blocks, and for each query block, the tables within the from clause are processed. When there's more than one table in a block, permutations of join order and join method are evaluated. Go back to the paper that we referred to by Jark and Koch, and remember that it is important that we join tables in a certain order, or we access tables in a certain order, so that subsequent steps have smaller quantities of data that will need to be operated on. This is what we're talking about in terms of permutation of join order. If we have 3 tables that are going to be joined, we could join table 1 and then table 2, then later bring in table 3. Or perhaps we could join 2 and 3 first, produces a smaller intermediate result, making the subsequent join with table 1 much less work. So this is the relevance of some of the material we presented earlier in our discussion. Once the execution plan has been determined, the code generator will take the steps that need to be performed and not write code from scratch, but basically they're extracting kind of canned routines for access methods. For example, the process of doing a matching index scan is a generic set of operations. It's kind of pre-built code. All I need to know is against which B tree index structure do I actually execute this code. So the code has been effectively pre-written. We're simply plugging in values for the actual objects. So control then will be immediately transferred to the code for interactive SQL. In the case of embedded SQL, SQL statements contained within a program, such as a C program or a Java program, the code is stored in the database for later execution. For additional information about what has been presented in these 2 videos, we give you some very useful references here. The Ubiquitous B Tree by Douglas Comer was a paper that we referred to in our first video. The paper by Jark and Koch, also listed here as a paper that appeared in the ACM computing surveys. We mentioned a couple other papers that would also shed light on the internal workings of a relational system and query optimization. This paper by Chaudhuri is a very good paper, providing an overview of query optimization, and the paper by Selinger was written based upon work done in the IBM prototype called System R. With these 2 videos, I hope that you now have a sufficient understanding to appreciate the complexity and challenges of arriving at an efficient execution plan. That's the role of the query optimizer. In fact, this area is something where all of the problems have not yet been solved. Continually, research is being done on improving query optimization. There's much more that can be said about using an index than what I presented in these 2 videos. But again, I'm hoping that you have a feel or an appreciation for what is involved with query optimization and how it contributes to the overall performance of a relational database.